Oh, yeah, yeah, now's a good time to turn me on. Okay. I'm putting on my microphone. I always feel like I'm dressing in front of people. Hi. Okay, well, we had a guest lecture last time. I think that was kind of fun. You saw some applications of neural networks, and what was he doing? What, come on, what was he doing? The guy that talked last time. What was he doing? Yeah, the general problem. What was he doing? From chemical sensors. Yeah. And he was trying to use a neural network actually to do the classification, to have it being the classifier, which was kind of interesting. All of his neural networks had a binary output? That could very well be. Well, in the sense that they were classifiers, that they had to classify a certain result. Yeah.
He was using a very small, he was advocating only ever using one hidden layer with a very small number of neurons.
Yes, which I did not agree with. Yeah.
Seems like the number of outputs could not be. Of course, he made no comment on it because it's not part of his problem area.
Yeah, he did use a lot of neurons for the outputs. The rule of thumb is that, of course, that the input dimensions are what give you the cursor dimensionality and not the outputs. But you do put a strain on the neural network because what you're trying to do is you're trying to have those hidden layers fit all of these different outputs at the same time. So there's a strain in that sense, but it's not as critical as the cursor dimensionality is in the output. Yeah, it would have been nice if maybe he would have talked a little bit more about that. Well, I think today we will do some other things. I wanted to point you out, by the way, to the web page and some of the resources which are available there to you. I do want to mention that on here, I know you cannot read this, but you can probably do pattern recognition so that when you come here, you can see this general shape and go, ah, there it is. I do have on here Fuzzy Sets by Latvizada. This was the original 1965 paper that Zada did. And it's probably been referenced a million times, not a million, but literally thousands of times, and is a seminal paper. And what's interesting about it, as is the case with many of the classic papers, it's enormously readable. I invite you to just sit down and read it, and you'll find out that much of what we presented here is taken almost verbatim from Zada's original paper. It was written so well. Claude Shannon's original 1948 paper in communication theory is that way also. When you're taught a course in communication theory and entropy and all that other stuff, they usually step through Claude Shannon's way of doing things. So Jim Bezdek, who is the past editor-in-chief of the IEEE Transactions on Fuzzy Systems, talked about this paper as being very inspirational to him and a place where people could go even today and look at the paper and get ideas for research. And you'll find out that indeed, as you read this paper, there are some ideas which Zada presents way back in 1965, which have remained somewhat unresolved. So it's a very fascinating paper. So I recommend it to you, although it's not a requirement. I think that it will spruce up your understanding of fuzzy sets. And Zada likes to distinguish that this paper was not about fuzzy logic. This was fuzzy sets. Now, he has to have fuzzy logic in order to manipulate those fuzzy sets. But notice that it is indeed fuzzy sets. There's another paper here, another classic paper, written by me. No, this is not a classic paper. What this is a paper which overgoes in a textbook sort of format the example that I did in class about GREs and GPAs. Hopefully you've discovered it and had a chance to look at it. So this is in lieu of a text. This fuzzy inference machine is not available. I have not made it available to you in a text, so this write-up will do in lieu of that. Okay? So those are some of the resources that are available on the web. And I took I like a lot of pictures when I read a paper. Do you like a lot of pictures? Okay, so I did a lot of pictures. Remember these pictures? This was the set of numbers close to integers, the set of numbers close to 2, and the ands and the ors. So all of that is in there, as well as this idea. And unlike my slides, I actually am able to, on here, give a very nice example of the GREs and the GPAs. In other words, we look at the GREs and the GPAs and the defuzzification, and it's done very, very precisely, and hopefully in a very, very clear instructional manner. At least that was the purpose in what I was doing. Today I want to finish some of the concepts which are in the book. One of which is that we have been going over is different ways to train artificial neural networks. And we talked about, for example, the different training techniques. Quick prop was one of them, which is available, for example, in your QuickNet program. We also talked about Jacob's delta bar delta rule, which was based on the heuristics that Jacob put forth, that if you are on a flat area that you want to take in your search process, teeny tiny steps, if you're on a very, right? No, if you're on a flat area, you want to take big monster steps. If you're on a steep area, you want to take teeny tiny steps. And notice the concept of big monster steps and teeny tiny steps are fuzzy linguistic variables, which leads us to the possibility, which is talked about in your text, of fuzzy control of error back propagation. Fuzzy control of error back propagation is in your text. Where is it? Faster variations of back propagation. Yes, on page 147 or there around. The idea is that we set up a set of tables wherein we can have the ability to optimize in accordance to some linguistic rules. If you're on a flat area, you want to take larger steps. If you're on a steep area, you take much, much larger steps. This is a classical sort of control problem. In fact, what we can do is we can look at the error which is generated by the neural network, and we can actually look at that error and the change in error. Remember with the induction machine that we looked at, we said that many times in fuzzy control that the things we looked at were the error, especially for tracking problems, and the change in error. And then we applied to those some sort of fuzzy linguistic rules. Well, here's an example of change in error and error for a fuzzy backprop. And what we're going to do is we're going to fill this in. We're going to fill this in for what do we do with the step size increment that we could have. What do we do with the increment? And here is what a table which has been suggested. Now these are standard sort of abbreviations for changes. The PS is positive small, negative small, and 0. We don't want to adjust the parameter of the step size in a gross fashion. We'd like to do it in a very small fashion. So the idea is that if our error is low, well, you can see here, for example, if our error is high and our change in error is high, then we would like, what happens? We're going down the slope, right? If our error and our change of error is high, if both of them are, we're going down the slope, so we want to make our step size smaller. So we want to adjust the step size a little bit negative small. Okay? And so you can see that as we go through here, this is exactly the sort of heuristics that you would expect with a fuzzy control. By the way, this is in the text in, let's see, introduction, fuzzy parameter. Yeah, if we could go to the overhead here, please. The third paper, now I don't want you to look at, well, I'm not going to hold you responsible for the entire paper. I'll never tell you not to look at anything. But this is fuzzy parameter adaptation and optimization. It turns out that all optimization algorithms, except maybe quick prop, have parameters which you adjust. Okay? And these are the smithing sort of things that one does. Well, all of them, in just about all cases, for all neural networks, not only the layered perceptron, but for something called the adaptive resonance theory neural network, which we haven't covered, the Cohonan neural network, which we haven't covered. They all have parameters which can be adjusted by heuristics. And these heuristics can be always encoded in fuzzy linguistic variables. Here is the result that was used for this. Let me see if it's actually better on the screen. It's a PDF document. Oh, that's terrible, isn't it? Okay, well, it's there, but it isn't that good. Okay, here we have, for example, the error. Here we have on top, this is the error, and this is the fuzzy membership function. This is an error of 0.2, 0.4, my hair, 0.8, 0.6, 0.8. Now you notice we can always look at this change in error because we're running the output neuron through a sigmoid, so therefore its dynamic range is indeed adjusted, and we have something to keep our hands on. So this is the actual error, the fuzzy membership for the error. This is the fuzzy membership functions for the change in error, and this is the consequent membership functions for negative 0. 0 is this triangle here, and then positive small. So in adjusting it, we use the typical, the exact same sort of fuzzy inference engine that we talked about with GPA and GRE, and also for the tracker to actually adjust the step size in these in the error. And typically it's much better than just keeping a static step size, as you can imagine. And here was an example that was used, and I'll actually show you something more interesting, a more, where'd it go? It's on the next page. Okay, hold your taters. There it is. Okay, if we can look right here. This is actually a, just for an example of learning a 3-bit parity problem. The exclusive OR is a 2-bit parity problem, if you think about it. If you have a 0 and 0, if you talk about even bits parity, that's 0, right? 1 and 1 is 0. 0 and 1 is odd bits parity, which is 1. So this is the extension of this concept to 3 bits, and it also holds with many other ones. This was a particularly drastic example because the backprop here, the backprop, as you can see, was very, very slow in the convergence. This is the Jacobs delta bar delta rule applied, and this was a fuzzy backprop. So it worked very well. But you always need to be suspicious when you see curves of this type. Anybody suggest reasons why you have to be suspicious when you see curves of this type? Number one is that any time you see these error curves, they're going to be stochastic. Why are they stochastic? Because your initialization is stochastic, isn't it? So therefore, if you had a different initialization, you might have a different result. In fact, your initialization might be exactly the correct weights. That'd be cool, right? And it could be. I mean, there's a finite, albeit very, very small chance that your initialization could be very, very near the original weights that you want. So therefore, when doing curves of this type, the thing that you have to be careful about, especially if you publish them, is to make sure that you let people know that these are very typical curves, or that you actually run the problem a number of times and average them so you have some statistical certainty that indeed these are typical representative curves for what is happening. In fact, the editors of both transactions and neural networks and evolutionary computation won't publish single curves. You have to establish that these are typical and assure that the readers that they are indeed typical. You could, but you get the result, which is just the same initialization for all three. It could be a different initialization, that one technique would work better than the other one. And in fact, with a good chance, that's true. Another reason is you're trying to make a general statement about the algorithm, and if one example doth not a generalization make, so we need to be careful in that sort of sense. Now, like anything, one has the ability to extend these ideas to more complicated areas. Let me tell you a interesting piece of work that we did on Neyman Pearson optimal detectors. If you're familiar, if you've taken I think Professor Ritchie teaches it, course in hypothesis testing, you usually have things such as your observed signal is simply noise, or your alternate hypothesis, which is that a observed signal is equal to a signal plus noise, right? Now, this is just like all of the hypotheses that we did before, because before we did hypothesis number 1, it was a shrub. Hypothesis number 0, it was a bush. So in any sort of classification problem, you can always break them down into hypotheses. Just like in any hypotheses, you have a trade-off between your false alarm and your detection probability, right? And if you can give me a detector, remember the little detector? Here's a detector. And you design the detector, and you put in Y, and you give a decision. That is a H0 or an H0. This might be a red bulb, and the other one be a black bulb? No, not a black bulb, green bulb. Okay. Here's H1. We're being attacked by enemy missiles, red light. Or H0, which is a green light, which says everything is okay. This is your detector. You build this detector, and there's numerous ways you can build the detector. As I mentioned, you could always have the green light on, right? In which case you get a lot of, if you always have the green light on, you get a lot of false alarm, but you get 100% detection, etc. Each one of these curves, if you build a little rule in here to turn on H0 versus H1, you have an ROC curve, which is this curve, which is beta versus alpha. And if you remember the curve, let's see, beta can be 100% if the alpha, let's see, no, 0 and 0. Yeah, 1 and 1. Okay. So the curves always kind of look like this. And in fact, you generated a few of those ROC curves using the Fisher discriminant as a technique for determining between one of the two classes. There is a theory, which if you take Professor Ritchie's class, I think it's Professor Ritchie, which is the Neyman-Pearson. I'm not sure of the spelling here. The Neyman-Pearson detector, which says this is the detector which you can generate in some cases, not all cases, but you can generate in all cases, which is the best detector that exists. The Neyman-Pearson detector for a given alpha maximizes beta. So if you give me an alpha, if I use this Neyman-Pearson detector, then I will maximize beta. So if I have a Neyman-Pearson optimal detector, it's the best I can do. I can't do any better, no matter what you do. Now, unfortunately, for all different hypothesis statements, one can not always generate a Neyman-Pearson optimal detector, but there are certain cases where indeed you can. If you have a Neyman-Pearson optimal detector and you come to me with any other detector, your ROC curve will be down here, always. In other words, your ROC curve will always be below the Neyman-Pearson optimal detector. Now, one of the places that Neyman-Pearson optimal detectors exist is for the case where you do have noise and you have a constant signal plus the noise, and you're trying to differentiate between the two based on 20 examples or 50 examples. So you get 20 or 50 examples which are coming in, these 20 or let's say 50 examples, and from these 50 examples you have to make a decision whether all of those 50 samples are noise or all of those 50 samples are signal plus noise, right? You with me? And so in those cases, you have name and Pearson optimal detectors. That exists for those sorts of problems. So one of them was in the area of Laplace noise, and there are two closed-form solutions for name and Pearson optimal detectors. In many cases, we know they exist. We can actually set them up, but the performance analysis of them is very, very difficult. It's terrible. And there's two closed-form solutions to them. One is the Gaussian, which everybody teaches, and the second one, I'll brag a little bit, was one that we developed for the case of Laplace noise. Those are the only two known closed-form solutions. Now, I will get to, with Professor Ritz, and he says closed form doesn't mean anything, because he says, I can do this by doing a little contour integration. I said, yeah, but yours is a numerical approximation. Mine's exact. So we go back and forth. So anyway, two closed-form solutions. So this means that for the Gaussian and for the name and Pearson, we have, for the Gaussian and the Laplace, we have name and Pearson optimal detectors, and they exist, and not only that, but we can actually write down equations that describe the ROC curve based on those. Not empirical, not a Monte Carlo sort of simulation, but actually analytical expressions that exist here. Well, one of the questions that we wanted to ask was, wonder what would happen if indeed we were to train a neural network and we were to try to train it in supervised learning of whether an input had noise or didn't have noise. So we had a signal, and so what we did is, this is the neural network emulation. So we had our 50 samples here. First thing we put in is 50 samples without noise into a neural network, and we gave it an output of 0 because it didn't have any signal associated with it. Then we put in 50 samples with noise. The noise is all different in all the cases, of course, but the signal is the same, very small. And then we trained the output to be a 1. And then we continued this process of training the neural network for whether the input was just noise, just random numbers poking along there, in this case generated from a Laplace random variable, or whether all of these samples were both noise and a little bit of a signal. And then once we train this, as you know, when we generate this neural network, we generate an ROC curve, because it depends once we train it in the actual playback. We set a threshold, and this threshold, if you remember, puts us on this ROC curve. So it is one of the detectors that we can do here. But we know we can't do as good or any better than the name and Pearson optimal detector, right? Right? So the question is, how well did this learn? Well, the results were really remarkable. The results were that the actual neural network had an ROC curve which actually butted up against the name and Pearson optimal curve. It was, we were really quite astonished that it was able to do that. But indeed it did. So it worked very, very well. So this was a very interesting problem. Now, another interesting problem is the way that we trained this. We chose not to train it with batch, where we only took, say, 50,000 examples of just noise, or signal plus noise, noise, signal plus noise. Every time we presented a sample for the neural network to learn, we generated it new. Why not? Random number generators are very cheap, right? And we can generate noise on the fly. So we would actually flip a coin and say, okay, this time there's no noise. There's no signal. There's always noise. There's no signal, so we just generate noise. We'd flip a coin again, say this is just noise, give it noise. Flip a coin again, this time we have a signal, so we'd put in a signal plus noise. And just continue flipping the coin, and every time presenting a new type of noise associated with the problem. Now, this is the online sort of training as opposed to the batch training, since we chose to update it every individual result. Now, the question, what was interesting, although it did emulate the name and Pearson optimal detector in terms of performance, the challenge was that it took forever to train. It took forever to train. And so what we attempted to do is to apply the same problem using fuzzy backprop. And here's the examples to this. First of all, This is the heuristics for the rule table. We still have the error and the change in error, but we have tessellated the rules a little more finely. In other words, we have specified the rules a little bit more precisely. And as before, we have the, so here are the rules, and then we have the change in error, and actually what we found out worked very good was not the change in, or the error and the change in error, but the change in error and the change in the error. So in other words, the first and the second derivative, and it worked really, really well for this. Well, applying this was the original training for using online training using this Laplace sort of result. And this is a typical example. And you'll notice that every once in a while there's a great big bump here. And this is the sort of thing that we would have expected if we were to have situations where we had online training. And so that was regular error backpropagation with the step size fine-tuned in such a manner that we saw it converge as fast as possible. Then we have the Jacob's delta bar delta rule, and it was actually much better. It doesn't look a lot better, but you'll notice especially in here, if you trace down the envelope here, this envelope is much higher than the envelope here, so this actually converged very, very quickly. And with the fuzzy backprop, it did this way. Okay. So the fuzzy backprop worked very well. In each of the cases, we tried to fine-tune the parameter so that we got the best performance. This does not say that fuzzy backprop is going to work better than all of these other techniques. Also, this was done prior to popularization of the use of quickprop. Quickprop. Is that the one I'm thinking of? The algorithm. What's the name of the software? I get the software and the algorithm. One's quickprop and the other one is fastprop or QuickNet. Okay, QuickNet's a software? Okay, quickprop is the Fallman algorithm. And never tried the Laplace thing with the Fallman. It would be fun to see how it did with that, because the Fallman algorithm for quickprop is kind of the default one that we go to many times because it works very, very well. So those were some examples of fuzzy backpropagation, and it's very interesting because it's a very simple example. It's no brain surgery here. That the concept that if you're doing searches, again, you want to monitor your steps and as a function of how quick you're going downhill. So it's straightforward in that sense. Now there's another algorithm. This is interesting. We have just covered fuzzy control of error backpropagation, right? Okay. Now I want to do backpropagation training of fuzzy control. Let me say that again. Okay. We just did fuzzy control of backpropagation. Now we're going to do backpropagation adaptation of fuzzy control. What we did here was actually look at adaptation and control the step size in accordance to how big the steps were, right? Now we're going to look at the opposite case, and this goes way back to when we talked about fuzzy inference. Remember, way in the beginning, I made a claim that if we were to use fuzzy inference, that the actual fuzzy inference engine, once it was tuned, was kind of insensitive in many cases to your choice of membership functions, your choice of logic, and that no matter what you did, it kind of worked if you were able to tune it. Now, how can you tune a fuzzy system? Well, you can do as was done in here by actually twiddling the membership functions and looking at different shapes of the membership functions. And you have a lot of parameters that you can twiddle. You can not only use triangular membership functions, you can use Gaussian membership functions, you can use different shapes of membership functions. You can control where they are centered, how wide they are, how many you have, etc. So there's a number of parameters which can actually be adjusted. So one of the ways, once you have a fuzzy inference engine, to make it work better is you begin to apply it, you begin to test it, and then you begin to tweak some of the different parameters to get a better result. If you know what your output should be, and you know what you want, and you know what you should get, then you should be able to tweak the things in order to get a better result. Again, you can do this with a man in the loop, or alternately, you can do it Alternately, you can do it using kind of a back propagation sort of sense. And let's go ahead and take a look at this, because I think this is very, very fascinating. Here's the basic idea of tuning of a fuzzy inference engine. I'm going to draw this, and please maybe try to copy it down. Here we have the antecedent. So we have the antecedent number 1, and we have the antecedent number 2. And so we have these tessellated in some fashion. And this is the fuzzy rule table. This is the fuzzy rule table. I've gone over this before, but now we're going to go over it a little bit more in detail, and since we have error back propagation under our belts, we'll be able to understand it better. Say that there's some things here which correspond to 0, and to positive large, say, for example. And there's going to be some other terms in there, but we're not going to deal with those at this point, just for illustrative purposes. Now, remember what we do. The first thing we do is we look at the actual results of antecedent number 1, antecedent number 2, and we fuzzify it. So we have all of these antecedents here. Let's call this E for error. Now let's call it GRE. And let's call this GPA. Okay. So we get this these different antecedents, say, what do we say? Low, medium, high, excellent. Low, medium, high, very high. We don't have to have the same results for everything. In fact, the actual rule table doesn't have to be square. We just choose it to do that way. Okay. So what do we do when we perform the fuzzy inference? If you recall, what we do is we take the antecedent number 1 and we fuzzify it, and we get numbers for each one of these, correct? We take this antecedent, we fuzzify it, and we get membership functions for these. Then, what's the next step that we do? We smear these this way, we smear these this way, and take the minimum. Take a Cartesian sort of product, but do the minimum in each one, because the original rules read that the change is 0 if this antecedent is medium and this antecedent is medium, so we use minimum for the logical and in order to do that. Then, according to a OR sort of aggregation, we say that the result is near 0 if this is true, that is if medium and medium, or this is true, high and low, right? So in the antecedent world, we would take 0, and we would take all of the different ones. Let's see, positive large would be way out here. And what we would do is as follows. We would take what operation? A maximum operation, correct? So we would take the maximum of these 3 numbers, and the maximum of those 3 numbers would go here, correct? We would similarly take the zeros, and we would take the max of these 2 numbers, and we would put it here. Now, each one of these correspond to a weight on the resulting membership function. So our resulting membership function, we would have some other results here, but I'm just doing the 0 and the positive large. So we would have membership functions for all of these results. And what we would do is we would weight whatever value here, at least in the form of the weighting defuzzification, whatever this value is here, we would weight this result. Does that make sense? And we would have a weight here, we would have a weight here, and then we would have a final weight here. Let's just say that the positive large won the day here. Now what would we like to do? We would like to perform a defussification. How do we do the defussification? We take some sort of central tendency of these membership functions and call that a result. Okay? So let's suppose we did that. Let's suppose that we did that, and let's suppose that we used the mode method of defussification. Normally, it works better if you take a center of mass or a medium or something. Let's take the mode here. That is the maximum value. So in this case, the mode is clearly this positive large. Okay? This positive large. And so the actual solution here would be, if this was on a scale of 1 to 10, maybe the guy would come out a 9 or something like that. Okay? So that would be mode defussification. Now, here's the situation that we have. You look at this, and you look at the GRA and the GPA, and you say, man, a guy with this GPA and GRE isn't that good. This is too big, right? This guy should be an 8. So this is just exactly like a neural network, where this is your output, right? This is your output. And what is your input? Your input is whatever these are, but you also have a target value. You also have a target value which might be equal to 8. So your output, which we'll call y to be consistent with the neural network, your output is a 9 and your target is an 8. So therefore you have an error of 1, right? Now the question is there a way that we can adjust some of these things using, for example, steepest descent, right? Can we do that? Specifically, if we have an error here, and this error on the output is equal to, in a batch sort of sense, y minus t squared, let's say 1/2 y minus t squared, what do we need to do if we would like to adjust one of the parameters up here? Well, the parameters up here, what do we want to adjust? Well, anything in the entire problem that you could move is something you can adjust. If you're able to assign a weight shape, you could do that. Maybe you could even do, remember, what was it? Jaeger ands and ors, they had a alpha parameter in them or a lambda parameter in them. You can adjust those. Don't adjust the actual logic that you're using. But the question is, how do you do that? Well, let's actually go up here and let's take a look at, for example, if we would like to adjust the membership function for the antecedent here for positive large. So we have the antecedent fuzzy membership functions, which are here. So this is low. This would be medium. This would be high. And this would be very high. So we could adjust these actual membership functions by adjusting, for example, two things. We could adjust the width, and we could adjust the corresponding centroid. Those are two parameters we could adjust, right? And instead of weights in a neural network, we can take this error and use this error in a steepest descent way to take each of these widths here and each of the centroids of each of the antecedent membership functions and adjust them using steepest descent. If we did this and we wanted to adjust this by steepest descent, what would we need to have? We would need to have the partial of E, the actual error out here, with respect to this centroid. And we would need the partial of E with respect to this weight. And if we had those, we could choose a step size, and we could adjust these two parameters so that we take a step downhill and get a better result. Does that make sense? The question is, how do we do that? Is there a way that we can do that? Yes, we can do that, and what is really delightful is that the way that one does this turns out to be very, very clean, as we'll see in a second. You can see that if we take a partials, we begin to, if we use error back propagation, which we can here, the first thing that we do is we get an error with respect to the target. I'm sorry, with respect to the output. Okay. With respect to the output, and of course that's equal to y minus t. But we don't want that. We also want the partial of the error with respect to each of the antecedents. I'm sorry, the consequence. Now, what is the consequence here? It is equal to the maximum of this, excuse me, this membership function, this membership function, this membership function, etc. So we want to actually take the derivative. I'm sorry, I forgot the derivative of the maximum. We want to take the derivative of a maximum with respect to these values. We actually talked way back a long time ago what the derivative of a maximum was. Do you remember what it was? Remember what this was? It's equal to 1 if x was the maximum and 0 otherwise. So the derivative of the maximum is equal to 1 if x was the maximum and it was equal to 0 otherwise. Do you remember us proving this in class here? Okay. The idea is if you have an x and a y here, right along here is the value x is equal to y. Over here, x is equal to the maximum. Over on this side of the dashed line, y is equal to a maximum. So if we take a partial of x with respect to x on this side, we get a 1. If we take a partial of x with respect to y on this side, we get a 0. Yeah. It's a discontinuity there. It's like asking what is on a unit step the value right at the step. And so it's undefined. You can put it anywhere you want to. That's basically the idea. Yeah, so we have 1 here. We actually have a unit step, and this could actually be written as a unit step of x minus y would be one way to write it, where u is a Heaviside unit step function. Okay. And by the way, if you actually looked at the original function, you would find out at x is equal to y, you'd have two planes coming up and hitting at a cusp. Actually a linear cusp, and there's really no definition of the slope here, right? If you have two lines which are coming up like that. So it's really undefined. I think a purist would probably set it equal to a half for reasons which we can go into. So that's equal to that. So what does this mean? This means that the partial of y with respect to each one of the consequents is equal to 1 if the value was the consequence, and it's equal to 0 otherwise. What this means is that the derivative, we can think of these as kind of light bulbs. The derivative is equal to 1 if this was the maximum. It's equal to 0 if it wasn't. So all of a sudden in the partial derivative expansion we go here, and it's kind of like this is the light bulb that lights up as the partial of y with respect to all of the consequence, because it's the maximum of all of these. And all of these other ones are 0. Make sense? So we have this. Now we need to take the partial of this with respect to where it came from. Now you notice that the positive large, and let me actually use the positive large here. The positive large is equal to the maximum of positive large 1, positive large 2, and positive large 3. Right? Which again, if we want to do now the rate of change of the consequent with respect to this positive large that we generated, what do we get? We get 1 if the P sub L was the max, and we get 0 otherwise. Now, what does that mean? That means if we come back here, and this, for example, had a 0.2, this one had a 0.6, and this one had a 0.8, which one of these gave rise to this value? This is clearly going to be 0.8. But where did this come from? This came from the 0.8, right? So if we backprop again and do the partial derivative of this with respect to all of the places it came from, one of these lights up as a light bulb, right? And which one of these lights up? This one. Whichever one is maximum is the one that lights up. Okay, well, you notice what we're doing. We're putting together a chain rule. The partial of the error with respect to y, the partial of y with respect to the consequent, the partial of the consequent with respect to positive large, which happened to be the one that gave us the maximum. Now what do we want to do? We want to do the partial of this. Let's call this partial 1, 2, and 3. We want to do the partial of positive large 1 with respect to the two things that gave rise to it. What is positive large 1? Positive large 1 is equal to the minimum of this antecedent, GPA high, and what? GRE excellent. Right? This value came from here, and maybe this originally was a 0.9. Now say this was a 0.8, and this one was a 0.9. And so how did we get this? Remember, we took the minimum of this with respect to this. So this value is equal to the minimum of this and this. And we want to do the partial. What's going to happen? It's going to be a pointer again. And that pointer is going to, in this case, be pointing to high because that was the minimum. Right? So just like the maximum, except different. This goes to the GPA high because GPA high was the minimum. So you see, the wonderful aspect of Zada logic is that in terms of differentiation of maximums and minimums, every time you do that, everything that contributed to a maximum, if you take a partial, points to the component in the derivative that gave rise to the maximum. If you take a partial of a minimum of a bunch of strings, you're going to get a pointer which points to the source of the minimum. Everything else is 0. So that's the reason in this mode declassification we had this pointing to here because this was the maximum, this pointing to here because this was the maximum of these three, and then this one pointing to here because it was the minimum of these two. So the min-max gives us a very nice pointer sort of adaptation. Well, now what do we have to do? Well, this high actually corresponds to a membership function. And it has a mean with a high and a width with respect to a high. Right? This is the membership function for GPA high. Well, there's a way that we can write that. We can write mu of GPA high as a function of x as equal to what I'll refer to as a triangle function of x minus its medium for high divided by its width for high, where the triangle function unscaled looks like this. Okay. Wait a minute. Okay. So what is the derivative of the triangle function? The derivative of the triangle function is a little pulse with a value of -1 here, a little pulse with a value of +1 here. So that's what the derivative is equal to, right? And then if we have, if we would like to do now the next step, which is the partial of GPA for high 1 with respect to M, well, we do this result. We get minus, using the chain rule of differentiation, minus lambda prime of x minus mh over wh, where the minus comes from differentiation of the argument, right? And then we get the width as the derivative of this with respect to the width. It looks like an x minus mh over minus wh squared. Is that right? So we do that also. Do you all see what I've done here in terms of the partials, the derivatives? It's using the chain rule of derivatives for calculus.
64 major crack failure incidents, they looked into that. Again, fatigue, corrosion, plus corrosion, crack, corrosion, fatigue, plus corrosion.
So let's put this all together as we begin to adjust by steepest descent the parameters for the input antecedent membership functions. By the way, we've chosen the input antecedent membership functions because they're easy targets. And they're also what is typically adjusted by people when they put themselves in the loop to adjust the problem. What do we want? We want the partial. Well, let's see. We have the partial of E with respect to Y, partial of Y with respect to the consequent, times the partial of the consequent with respect to the positive large, which we found out was the result there, times the derivative of the positive large with respect to, say, the median, the mean. And we found out that this all, if we use the chain rule here, is equal to the partial of the error with respect to the median, which is what we want for steepest descent. Now we need to fill this in. This tells us a step that we get downstream. What's a partial of E with respect to Y? Well, that's Y minus T. What's the partial of Y with respect to const? Well, the derivative of any maximum or minimum function is either 1 or 0. And because of the pointer, we're pointing in the direction where we're going, so that's equal to 1. This is also a maximum, so that's 1. This is also a maximum, so that's 1. And then finally we have, did I forget something? Yeah, did I get that wrong? GPA, PL, I forgot here. DPL1, DGPA. That's what I forgot. Thanks. DPL1, DGPA, and then the last one, DGPA times the partial with respect to M. By the way, all of the details for this are spelled out in the paper, which is available to you. So anytime you differentiate with respect to a max or a min, you get either 1 or 0, and we don't even keep track of the zeros. We just keep the ones. Those are the pointers that point us back from whence we came, and we're left with the partial of the GPA with respect to this, which is minus lambda prime x minus mh over wh. So this is the result that we get for going downhill. So we can apply a step size to it and actually begin to adjust the parameters. Likewise, we can adjust the parameters for the partial of the error with respect to the width. So you get the general idea. Let me take a step back and try to do a gestalt so we're not totally wiped in the woods. Wiped in the woods? Lost in the woods. What does wiped in the woods mean? I have no idea. I don't want to know. Okay. Now this is for mode declassification. Okay. So we take the output, which is the maximum. So if we take the derivative of the output with respect to the maximum of a number of numbers, we get 1 if the result was the maximum, and we get 0 elsewhere. So therefore, taking the first partial takes us here to this, and all the other partials are 0 here. There's no reason we have to follow these partials back, because in the string of things, they're all going to be 0. We only have to follow this partial that's pointed to. Now, this partial was the maximum of here, here, and here. Same exact thing. This points back to the number that gave the result from here. And the actual partial is equal to 1 as it points back here, and is equal to 0 for here and here. Okay? So we go from here, I'm sorry, from the output to here, and we get this. This derivative here is actually equal to 1. We go from here to here, which is the maximum that gave rise to this. This derivative is 1. We go from here to here because this is the minimum of these two, which gave rise to this result. And then this corresponds to the membership function for this antecedent for the GPA. And so we can look at specifically at that membership function, and we can see that this is the one that we want to adjust. Let me do the converse. You know what we've actually discovered? That the only thing that was important to this output was this membership function. This membership function totally determined this output, because it happened to fit in right with the other ones, but nevertheless it did. Because why? This 0.8 came here, this 0.8 came here, and this 0.8 came here. Right? So it dominated the process. It went in a forward cycle. It turned out to be at the right max and minimum, but it was this value that found its way to the output. So if you want the output to be equal to a result, doesn't it make sense that you would want to change the single antecedent that gave result to the consequent? That's the one you would want to tune? Yeah, that's exactly what we found out through all these partial derivatives. Indeed, that this is the one we want to tune. Okay? So that's kind of cute.
Use some product logic, even though it'd be more complicated.
You could use some product logic, and you would come up with a different result. Yes. Now, what's also interesting, let me tell you a little bit more of the complications. If you use different types of logic, you do not get this pointer sort of adaptation we have here. You can see why we call it pointer, because it points directly from the min-max where it came from. And this is the nice thing about the Zada logic. If we were to use some product logic or another logic, the back propagation would be tractable, but it wouldn't be as straightforward and pointed as this. Another thing, notice we did, is we used mode logic, which is something that you don't use normally. Rather, what do? We take the actual average of these and look at the center of mass, remember? Now, if we actually took the center of mass, it means the center of mass had a correspondence, a contribution here, 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 and here. The center of mass had a contribution from all of those, right? So each one of these would be pointed back in some sort of pointer logic to the the antecedent that gave rise to it, and that would be adjusted all at once if you did that, okay? So if you use that sort of logic, yeah, it's a little more complicated.
Do you adjust just one parameter, or do you adjust both of them?
Oh, you adjust both of them, just like in a neural network you adjust all of the weights. Here, for example, when we get back here, I gave you an expression for adjusting the mean. Yes, you also want to adjust the width. Yes, you also want to adjust the width.
When you're using this for fuzzy back propagation, where do you get
Wait,
the
fuzzy, okay, we're not doing fuzzy back propagation, we're doing back propagation training of fuzzy rules.
Right. But if you're going to use a fuzzy system for the neural network training,
Okay, which is what we talked about at the beginning.
Where do you get the targets to compare
to who's to say what a good step size is?
Okay, well, that's a good point. The point is that we assume that once we have this fuzzy system, we have training data on which to tune it.
Because there's no one to say what the best.
I agree, and if you don't have training data on which to tune it, you can't tune it. You have to know the difference, you have to know the accuracy of your fuzzy inference machine. So you're 100% right. In order to do this, it is just like, and notice it's just like training a neural network. Remember I said neural networks and fuzzy logic were very, very similar to each other? It's very similar to doing this. This is kind of the output layer, this is kind of the hidden layer, the antecedents kind of take the place of the input layer. And there's lots of work on neural fuzzy sort of logic. And the nice thing about this sort of logic is that if you do train a system this way, you have a very nice ability to, once you're done, extract the rules from it. Remember we talked about the idea of a explanation facility. This is very nice because you do have an explanation facility once you get done, because you can actually espouse the rules to it. And it's just like a neural network, except that instead of, well, it's not just like a neural network, but it has the flavor of a neural network. The difference is, instead of initiating the weights of the parameters that you tune by random, you're initiating the weights and the parameters by heuristics, right? By fuzzy linguistic variables. And then once you have these initial parameters established by fuzzy linguistic variables, you train those variables, in this case, for the neural networks, the weights, in this case, the parameters for the membership function, in order to best fit the data in some sort of fashion. Can you use testing and training sort of data to make sure you don't memorize? Yes, absolutely you can. It's the same sort of animal. And the interesting thing is you have to take my word for it, is that once you get a system set up and you train it using backpropagation or whatever technique you do use to train it, it becomes relatively, not totally, but relatively insensitive to the logic and the membership functions you initially chose, because that logic and the membership functions will adapt around variations in order to better fit the results that you have. Okay, and that's true whether you do it in an automatic way like this. This is automatic. This is if you do indeed have training data, which you know the neural network or the fuzzy system wants to emulate. You can do it this way. Or if you have a person in the loop. Person in the loop is looking and trying to adjust these parameters and seeing what the results are and coming up with what they consider to be a good control based on their heuristics. Any additional questions? And you did ask about the different logic. Yeah, it gets more complicated with different logic. Yes, absolutely. But it can be done, and a lot of people do that. By the way, a lot of people like the more complicated logic because they like to see a lot of things tuned as opposed to little things tuned. Remember we said for a neural network, if you go with the maximum, you get in a whack-a-mole sort of problem? Remember that? You whack one down, you whack that maximum up, and one pops up, you whack it down, and the other one pops up. You can get into those sort of problems here. And that will be less if you actually spread your ability to adapt around the fuzzy system. Okay. Any questions? Yes?
The triangle function, you want WH to be the base, but your base is length 2 for the other triangle function.
Yeah, I would say it should. You like this better? Yeah, I was hesitant when I put this up there. I think this is I think you're probably right. I think this is 2WH here. It should be 2WH. Okay. WH is the one-sided width. By the way, one of the things that people many times do, which we've found very nicely, is to simply choose a number of points for the antecedents. And then with the antecedents, you can always choose membership functions which correspond to a membership function corresponding to these points. You get the idea? You can always choose these points and always draw membership functions in the fashion that we have shown here. And what you can do is when you backpropagate, if you just use these points, You can just adjust them if they correspond to the membership function that you're dealing with. So it's kind of nice in that sense. Whoops, I kind of screwed up here, didn't I? There should be a. No, that's right. See, the nice thing about these membership functions, they always add up to 1. And everything adding up to a possibility of 1, I like that, because it kind of makes sense, right? Another thing, notice, and then I'll let you go, is that the fuzzy system, here's a way of thinking about it, is looking at laying out results for all possible manifestations of the antecedents, right? And in fact, if you have training data, that training data might not even touch this region of the antecedent. You might do all of your training and do all the adjusting over here and here, right? But it still leaves your intuition intact for the possible outcomes. That's a nice thing too. Your heuristics survive the training, even if none of your training data addresses that problem. Okay, any more questions? No? Okay, that's it then. Thank you.